And our next speaker is Vikas, and he will tell us about planar graphs, more about planar graphs. Please, Vikas.
So good morning, everyone. Today I'll be talking about the complexity of pair domination problem in AT-free graphs and planar graphs. So this is a variant of well-studied problem in graph theory called domination in graphs. So let's first understand what is domination. Suppose we have a set of villages in some remote part of the country, and we want to build hospitals to provide medical facilities to the residents of the villages. Now, since building a hospital is very costly, so preferably we do not want to build hospitals in all the villages, but we want to pick some villages and we will build hospitals there. And we have a constraint that a person should not travel more than 10 kilometers to visit a hospital. Now, this problem can be modeled as a graph theoretic problem where each vertex will represent a village and two vertices are adjacent if the distance between the corresponding villages is at most 10 kilometers. Now, in this graph, we are interested in finding a subset S of vertices such that if a vertex is not in S, it should be adjacent to a vertex in S. So, formally, such a set is called dominating set, and formally a subset D of vertices in a graph is called dominating set if every vertex outside D has a neighbor in D. For example, in this graph, the vertices that are colored red forms a dominating set. This concept was introduced by Burge and Orr in 1962, formally introduced by Burge and Orr. Since if you take all the vertices of the graph, it will form a dominating set. So we are interested in finding a minimum cardinality dominating set of a graph, which is called minimum domination problem, and the minimum cardinality of a dominating set is called domination number, which is denoted by this symbol gamma g. It has applications in computer communication networks, locating radar station problems, and many more. The problem is well studied in the literature, and over 4,000 articles are published till date. So it has a lot of application and depending upon the applications, people have introduced generalizations and some variants of the domination. So today I am going to talk about a variant of domination which is known as pair domination. So in the previous example, these three vertices will dominate all the vertices of the graph. So suppose we want to pair each of the vertex in the dominating set with another vertex of the dominating set, so that in case of emergency they can make some communication or they can act as a backup for each other. So with this motivation, Heinz and Slater introduced the concept called pair domination. So in a graph with no isolated vertices, a dominating set is called pair dominating set if the graph induced on D has a perfect matching, and a pair dominating exists if and only if the graph has no isolated vertices. For the graph that is here, the vertices that are colored green forms a pair dominating set. Similar to domination problem, here also we are interested in finding a minimum cardinality pair dominating set, which is known as minimum pair domination problem, and the minimum cardinality of a pair dominating set is known as pair domination number. So several bounds have been established on the pair domination number. In 2009, Goddard and Henning conjectured that for a graph on n vertices where the minimum degree is at least 3, the pair domination number is at most 4/7 of the size of the vertex set. And some progress has been made on this conjecture. At the algorithmic front, the minimum pair domination problem on a graph with maximum degree delta can be approximated within the ratio of log of 2 delta plus 1, and it cannot be approximated within better than log of size of vertex set for any epsilon greater than 0 unless p equal to np. The problem is also known to be APX complete for the graphs with maximum degree 3. Since the problem is hard on the general graphs, people have considered special graph classes to study the complexity of the problem. So for the graph classes that is represented above the dotted line, the problem is NP complete, and for the graph classes that is on the below the dotted line, the problem is polytime solvable. The complexity of the problem remains open for like almost 7 years before we solve the complexity of the problem on planar graphs, and we proved that it is NP complete for the planar graphs. We also gave a polynomial time algorithm for the problem on AT-free graphs and an approximation algorithm for the problem on AT-free graphs. So these are the results that we gave. Like we also proved that for a given graph it is NP hard to decide if the pair domination number is exactly equal to the domination number. So what is an asteroidal triple graph? In a graph, let X be the set of 3 independent vertices. This set S is called asteroidal triple if for any 2 vertices in the set there exists a path that avoids the neighborhood of the close neighborhood of the third. So that this set is called AT. For example, in this graph, the vertices that are colored red forms an AT. And a graph is AT free if it does not contain asteroidal triple. So what is good about asteroidal triple graphs, AT free graphs, is that there exists a pair of vertices, special pair of vertices which is called dominating pair. And what is dominating pair? So a pair of vertices xy is called dominating pair. If you take any path connecting x and y, the vertex set of that path is a dominating set. And if you take the shortest path between these 2 vertices, that is called dominating shortest path. So in this example, V1 and V3 is a dominating pair, and the path V1, V2, V3 is a dominating shortest path. So using this dominating shortest path, we presented a 2.5 approximation algorithm for the problem on AT-free graphs. There is a special property of this AT-free graph that there exists for a like if G is an any AT-free graph with dominating pair x and y, and T is a BFS tree of this graph G rooted at x, and L0, L1, L2 are the BFS levels of this BFS tree, then there exists a linear time algorithm that computes a path x0 to xd such that each xi lies in the level Li and all the vertices at level Li is either adjacent to xi or xi minus 1. So using this property we are able to bound the number of vertices from any j plus 1 conjugative BFS levels that are coming in a minimum pair dominating set. And that is, we proved that there exists a minimum cardinality pair dominating set dp such that dp contains at most j plus 4 vertices from any j plus 1 conjugative BFS levels. And using this property we are able to design a polytime algorithm. We also studied the complexity of the problem in planar graphs. We proved that the problem is NP complete on planar graphs, and for this purpose we describe a reduction from minimum vertex cover problem, which is known to be NP complete for cubic graphs. So we take a cubic graph and we replace each of the vertices by this gadget that is shown here, and we proved that in the constructed graph G prime, the pair domination number of G prime is equal to 4 times the size of the vertex set of G plus 2 times beta G, where beta G denotes the minimum vertex cover of the graph. It is known that the pair domination number is sandwiched between the domination number and 2 times the domination number. So Alvarado et al. In 2015 studied the equality of this inequation, and he proved that it is NP hard to decide for a given graph whether the pair domination number is equal to 2 times the domination number. And in the same paper he conjectured that it is NP hard to decide for a given graph whether the pair domination number is equal to domination number, and we settled this conjecture in affirmative answer. Thank you.
Thanks, Vikas, for sharing your research with us.